All right, and the final section of this chapter deals with trends in the periodic table. I want to draw your attention to the word trend, okay? Let's say I said, oh, there's a trend in our class. Everybody's into neon hats. Well, if it's a trend, does that literally mean that every single person is into it? No, it would mean a lot of people are, but there could be exceptions. And so when you look at trends in the periodic table, I know all of you are very astute. You'll probably notice some exceptions, but we're just going to focus on general what? General trends within the periodic table. And the first trend we're going to look at is atomic radii. And an atomic radius is defined as the distance extending from the center of the nucleus of the atom to the location of the valence shell electrons, right? So if we have our atom that looks something like this, if this is where a valence electron is and this is our nucleus, the atomic radius is going to be this distance right here, okay? And you can see we have some of the elements from the periodic table. You notice that they put elements from groups 1 and 2 and then from groups 13 to 17. So we've left out the D block here entirely. These first two columns would be the S block and this would be the P block over here. The reason why we leave it the D block is because, like I said, the D block has a lot of exceptions, and so we're not going to stress about those in this class. But you probably notice right away that as you go down a group, you can see the trend, right, is that the atoms get bigger and bigger. Well, that stands to reason because their valence electrons are going to be in a higher energy orbital, right? So that means they're going to be further from the nucleus. And so it stands to reason that a cesium should be bigger than a sodium, et cetera, et cetera. So the trend is as we go down a group, size is going to increase. Now, here's the next trend, which you might have to think about this one for a few minutes, but I'm going to do my best to explain it to you, okay? And that is that atomic radius decreases going across a group, or going across a period rather, from left to right, right? Look, if you go from lithium to beryllium to boron to carbon to nitrogen, oxygen, fluorine, you can see the elements actually get smaller. And that's counterintuitive, isn't it? Right? Because you learn at the beginning of this class that matter is anything that has mass and takes up space. And you're saying, okay, well, if I go from, lithium to beryllium to boron, carbon, et cetera, I'm adding more protons, more neutrons, more electrons. Shouldn't it get bigger? It's a good point. Okay, it's a very good point. But remember, if you go from lithium to beryllium, right? Lithium has an electron configuration of 1s2, 2s1, whereas beryllium is 1s2, 2s2. So you notice that when you go to beryllium, you're adding more electrons, but they're to a 2s orbital, so the orbital is the same size. Okay, so we're adding more electrons, but to an orbital that's the same size. But what else are you adding? As you're adding electrons, you're also adding what? Protons in the nucleus, right? Lithium has 3 protons, but beryllium has 4 protons. So that means it's got more positive charge in the nucleus, and so it's going to pull the electrons in tighter. And so we see that as we go across the period. So we go from boron, which has 5 protons, to carbon, which has 6, 7, 8, 9, right? It pulls the electrons in tighter and tighter. Why? Because all of these electrons, the valence electrons, are being added to 2s orbitals and 2p orbitals for the boron, carbon, nitrogen, oxygen, and fluorine. So again, the reason why the elements get smaller as you go from left to right in a period, it's because, you're adding more matter, but you're also adding more electrons, but you're also adding more protons to the nucleus, which is going to pull those electrons in tighter and tighter. Come to Papa, right? Brings them in even closer. Okay, so kind of counterintuitive, but that's the way it works with atomic radii. Now, next we're going to look at ionization energy. Specifically in this class, we study first ionization energy. If you take a higher level chemistry class, it'll look at second and third and fourth ionization energies. But we're just going to study the first one. And if you're like, what is an ionization energy? It's the energy required to remove the first outermost electron from a neutral atom. So if you take the first electron, the first valence electron, if you pull it off of the atom, okay? So it's removal, taking an electron away, the first outermost electron from an atom. That's what the first ionization energy is. And so it always costs you energy to pull an electron off of an atom. So you see that all of these values here, all these numbers are positive, okay? But you notice the trend, the first trend that I want to point out is that, look, if you go down a group. I know the way that they describe it in the textbook is going up, okay? But I like to think of it as going down. You notice that the ionization energy at the top is high, but the ionization energy at the bottom is low. Well, didn't we say that the elements at the top are really small and that the elements at the bottom are really big? So that means that the valence electrons for a small atom are going to be very close to the nucleus, whereas the valence electrons for a large atom are going to be further away from the nucleus, and so they're not going to be as attracted to the nucleus, so they're easier to pull off. So that's why ionization energy decreases as you go down a group. However, you also need to know the trend for going across a period, okay? Now, I know that there's some exceptions here, but generally speaking, as you go across a period, so as you go from lithium to beryllium to boron, carbon, nitrogen, oxygen, fluorine, and yes, I see the exceptions too, but generally speaking, the numbers are getting bigger. Look, we're going from 521 to 1087, 1682 to 2080, right? Generally speaking, they're getting bigger, so that means it's costing you more energy. The ionization energy is increasing as you go across a period. Well, why would that be? Well, remember what we said. We said that as you go across a period, the elements get smaller and smaller and smaller. And so that means the valence electrons are going to be closer and closer to the nucleus. And so they're going to be more strongly attracted to the nucleus because they're closer to that positive charge in the nucleus. And so they're going to be more difficult to remove. And so ionization energy increases going across a period from left to right, and ionization energy decreases going down a group, going from top to bottom. And the last trend that we look at in this class is electronegativity. It's a lot of students' favorite trend, and it follows the exact same trend as ionization energy. You'll notice the ionization energy, which is right here, you'll notice it increases going up and to the right. And for electronegativity, you'll notice it's the same. It increases going up and to the right. It turns out that fluorine is the most electronegative element in the whole periodic table. Okay, it takes the gold medal. Okay, so electronegativity, what is it? It's a measure of the tendency of an atom to attract electrons. Okay, if I go into more detail, it's really if you have electrons participating in a bond. Okay, the more electronegative element is going to pull the electrons towards itself. But either way, it's a tendency of an atom to attract electrons. And so again, the trend for electronegativity is going to be the same as that for the first ionization energy. And that is that it increases going from left to right across a period, and it increases going up a group. All right, let's take a look at a question. Rank the elements barium, neon, molybdenum, and bromine based on atomic radii, first ionization energy, and electronegativity. So you can see I made a little sketch of a periodic table here, and I placed those elements. So we've got our barium, molybdenum, bromine, and neon in there. So if we go and we start with increasing atomic radii, well, which one of these is going to be the smallest? It's going to be the one, right, because size. So if we go with radii is going to increase going down, right? And it's going to increase going this way, right? So that means the biggest elements, so we'll put largest, are going to be found down in the bottom left-hand corner, and the smallest are going to be found in the upper right-hand corner. So it's going to go neon, and then bromine should be bigger than neon, then molybdenum, and then barium would be the biggest of all of those. Okay, so let me just erase some of this stuff. Okay, now we're going to take a look at ionization energy. So maybe I'll use a different color for that. So ionization energy, we said that it increases going up and to the right. And so we want to rank them increasing ionization energy. So the lowest one is going to be the barium, followed by molybdenum. Then we've got our bromine, and then we have our neon. Okay, and so that is the trend for ionization energy. And remember, the trend for electronegativity, sometimes I write EN for electronegativity, is the exact same as ionization energy. And so electronegativity is going to follow the exact same trend as ionization energy. So barium, molybdenum, bromine, and neon. Now, remember, you're going to want to do all the exercises at the end of chapter 2. When you go to the end of chapter 2, there's a whole plethora of problems that you can tackle there, okay, if you look at the exercises. And note, or just be reminded that the even number exercises have answers in Appendix B. And so that's why I recommend that students do the even numbered exercises in the textbook. So I'd start with question 2.2, then do question 2.4, 2.6, 2.8, etc., etc. And so what were our chapter objectives? Well, by the end of this chapter, you should be able to find elements in the periodic table. You should know what a group is and what a period is. So remember, groups are vertical, periods are horizontal. What else? I recommend reading the periodic table every day while you're in this class, just to familiarize yourself with the names of the elements, and their elemental symbols. Then you should be able to describe charge, mass, and location of the 3 subatomic particles. So you should know what a proton is and that it has a charge of +1. You should know what a neutron is and that it has no charge, and that an electron has a charge of -1. You should also know that protons and neutrons are about 2,000 times heavier than an electron. You should be able to write an atomic symbol for a given set of subatomic particles. Sorry, this is stuck up here like this. But anyhow, you should know mass number and atomic number. So mass number would be A, atomic number would be Z, and the atomic symbol would be X here. You should know what an isotope is. So remember isotopes, so let's say you have 2 isotopes of carbon. They have the same number of protons, but different numbers of what? Neutrons, right? Write balanced equations for radioactive decay. So you should be able to write a balanced equation for the radioactive decay, meaning giving off a beta particle or a positron or an alpha particle. What else? Solve problems using the half-life concept. So we talked about T1/2. So you just, for every half-life, you divide the quantity by 2. You should be able to describe a little bit of the applications of radiation in health and medicine. So make sure you read through section 2.5 in the textbook. You should be able to write out an electron configuration. So that's what we covered. 1s2, 2s2, 2p6, and all that good stuff. All the way up to element number 56. So that's as far as I expect you to do in this class. And so element 56 would be barium. So let me just see here. Element 56 would be barium. Okay, so you don't have to worry about F. Okay, I mentioned the F orbitals. I said we don't cover those in this class, so don't stress about them. And then describe periodic trends. So you should know the trend for radius, first ionization energy, and electronegativity, which were covered in this video.